Hi, this is Lucia DelVillano and Rachel Horstman, and we'll be going through the analysis of a convex parabolic spine.
To perform the analysis, we used NX 10.0 to create the geometry of the fin and used ANSYS Workbench to analyze the temperature gradient and the heat rate.
Moving forward with the analysis, we needed to determine a thickness for our fins. We did this by calculating the length using the length equation listed below for both aluminum and copper. We found that by using the thickness of 3 mm, we received a shorter length compared to a 6 mm thickness.
Now that we have determined a thickness of 3 mm, we used ANSYS to analyze fins of multiple lengths. The data collected, seen in the tables and graph, illustrates that the optimal fin length is 225 mm for aluminum and 300 mm for copper.
The best results from the data collection for aluminum were 300 and 225 mm, and for copper were 450 and 300 mm. We used a cost analysis to determine that the shorter lengths were optimal due to the reduction in cost. In order to verify standard equations for temperatures along a fin, we manually calculated the temperature at the midpoint of each fin and compared these values to the actual temperatures found at these locations using ANSYS. The percent errors prove the validity of these standard equations.
To verify standard heat rate equations, we manually calculated the heat rates at the base of each fin and compared these values to the actual heat rate found using ANSYS. These calculations proved that standard heat rate equations are valid because the percent error was around 10% for each fin.
Using the provided efficiency equation for a convex parabolic spine, we calculated the efficiency of the aluminum fin to be 52% and the copper fin to be 58%.
After analyzing all of our results, we advise that an aluminum fin of length 225 mm and a thickness of 3 mm be utilized. The aluminum fin is beneficial because it is a cheaper option with a comparable heat rate and efficiency.